Alright, boys and girls, welcome back to the drive-thru for a 2016 version of the drive-thru, sponsored by the deli. Hungry? Stop by the deli. Get a salad. I need a salad because all of those wonderful gifts that you guys gave me before winter break, now I'm fatter than ever, and it needs to change. Also, this is a first-time remix edition of 2016. When my kid asked me, "Daddy, how come I never get to see you?" It's because I always forget to turn on the microphone, Marley, and I'm sorry about that. So here we are, take two. All right, you are going to learn in this chapter that the volume of a solid is equal to the double integral of f of x comma y dA. So that's this section. And this section and this video will be dedicated primarily to setting these things up right. Okay? The actual integration, can either be very tricky, and I hope that when it's tricky you have a resource to fall back on, like your calculator, TI-84 or your TI-89 or your Inspire. Okay? Let's explain this formula a little bit more. So this is the definition of the volume of a surface. So notice that our plane region R has to be integrable and it has to be positive for all of these points in the region. That doesn't mean that the function has to be strictly positive, it's just got to be positive in the region. Okay, then the volume is defined, as I said, as V equals the double integral of f of x comma y dA. Now what's dA? Well, let's write it again in a different way. We could write dA as dy dx. If it was if in the xy plane the object was vertically simple, then we would choose dy dx. If it was horizontally simple, okay, it would be dx dy. So let's take an example of one that was horizontally simple. So now you're going to have to write two different pictures. You start with like an aerial picture. We said this was horizontally simple. So let's say it looked something like this. This was A and this was B. And we've got some functions that it's bounded by here. Okay, so that would be the aerial looking at it, and then here is the actual look at this thing. So let's see. This is the x-plane, so the y. So it would go, it's parallel to the x, so like this. And like this, and we'd have some functions here. So let's say this is f of x on the right and g of x on the left. And there A is positive, so this would be A and B. And then what you've got to envision, what we haven't graphed yet, is that over this region there is some roof. It's on fire. And that roof could have variable heights. It could be changing, but it is it's a surface. Okay, so here this is z equals f of x comma y for some region R. It is a surface. Well, what we are doing is finding the volume of that, oh gosh, funky surface. And those should all be vertical lines. Okay? That's exactly what we're doing. So, if I could just use a little bit better picture here, and just to break this down, V is the double integral of f of x comma y dy dx. Remember, anytime we find volume of a prism, we are multiplying length times width times height. So if I could use this prism, this here is the same thing as z. So z for that is right there. That's our height. This is our z. Okay? Think about dx would be right here. And you can see that dy is right there. There's dy. Okay? And what do integrals do? Well, this integral is kind of going to add up, let's see, that would be y equals. So that would kind of be adding up, it's kind of like the opposite order you're used to. All the areas of these rectangles right here, and then when we multiply by this, we're adding up all of those, and we're calculating all the volume. Okay, so see your book for a more detailed explanation of that, but hopefully you understand. We're just adding up a bunch of little products. Okay, so this is our first and only example of this video. Find the volume of the solid region bounded by the paraboloid. I got to add my exponents there, excuse me. Z equals 4 minus x squared minus 2y squared and the xy plane. So it's helpful here to first start by sketching the aerial. So when the xy plane is z equals 0. So what we have to do is get an idea of what is this going to look like. So we take a level curve at z equals 0. So setting z equal to 0, we get 0 equals 4 minus x squared minus 2y squared. So you get x squared plus y squared. So x squared over 4 plus y squared over 2 is equal to 1. I just kind of moved a bunch of stuff and divided by 4. So what that does is it lets us know that, let's see, x is going to go to 2 and negative 2, and y is going to go to radical 2, which is like here-ish. Okay, and that's what our paraboloid's going to, our parabola, that's the base of our paraboloid, is going to look like. Okay? Now, as you can see, we could consider this thing to be vertically simple, or we could consider it to be horizontally simple. We will just stick with dy dx for this one. So, now, we'll set up the integral. It's the double integral of 4 minus x squared minus 2y squared dy dx. So, we know that x is going to go from 2 to negative 2. So that's why I chose dy dx, so I didn't have to have radicals there. Okay? And so now, I've got to solve this thing to get my y's. So, actually, I won't solve that thing. Sorry. I'll solve that thing. So I get 2y squared is 4 minus x squared. Y squared is 4 minus x squared over 2. So y is plus or minus the square root of 4 minus x squared all over 2. Okay, so that would be the two sides of this parabola. This would be that, and this would be the negative version of it. Okay, so now we know that that y is in between those two limits. So, oh, I had that wrong. This one would be down here. So, this equation would represent this portion No, I had that right in the first place. No. That's good. That's good. These are my y's. My gosh. All right, so it goes from negative radical 4 minus x squared over 2 to positive radical 4 minus x squared over 2. Okay, so that's our double integral setup, our iterated integral setup, just like this. Okay, now at this point you could just pop that thing right into your 84, or maybe you'll get to a point where you'll get down to something that looks like you've used some x substitution, and you've got something that looks like this: 128 over 3 radical 2 times the integral from 0 to pi over 2. If you're wondering, how did I get pi over 2 when we started out with negative 2? Well, what we did was, in one of the steps, we substituted and let x equals 2 sine of theta. Okay? And that's just part of the really tricky integration that goes with these, which is exactly why we just want to use our technology. Here we would have cosine to the 4th of theta d theta. Remember, we substituted, virtually substituted in x equals 2 sine of theta, which is why now we don't have dx left anymore. We have d theta left. Okay, if you're confused about this, you're not confused about what's new. I hope that you all understood this, how we set it up. All I'm talking about now is how we would actually evaluate the integral, and this is for the people that don't know how to put this in their calculator. So, from here, you would just use this Wally's formula, which is from 7.3, and you end up getting 4 radical 2 pi, or 4 pi radical 2, and that's your volume. We'll have one more video to come on this, and what we'll do is we'll talk about how this applies maybe to a little financial concept, so we're not always just talking about volume, which is not that important, but multiplying things together and adding them up and finding maybe the average value of a region, that could be really useful. Boom!